Hi, everybody. So today we're trying to show you how you can turn in your BMC into a revolving door. So here there is Fabien Perigaud, Alexandre Gazet, and myself, Joffrey Czarny. If you need something more about us, everything has been already leaked on the internet, so feel free to go there. Sorry guys, it's not working. Okay. Oh, no, it's okay. Okay. Thank you. So, let's start for the first introduction. So, we're talking about BMC, so base management controller. So, we are focused on the HPA system, it's ILO BMC. So this talk was covers version 4 that has been ending until middle of 2017, but also we will introduce some part on ILO 5. About ILO itself, it's a standalone system, so there is a dedicated ARM processor, there is a firmware stored on the NOR chip, dedicated RAM chip, dedicated network interfaces, and the last but not least, you should know that if you plug the server, so if you make the power on the server, ILO start. You don't need to boot the server to that ILO need to be start. It's already start as soon as you plug the server on the power. About the design, one really interesting features on ILO is you have a direct access to the host memory. So it means that if you can have an access on ILO, you can reach with the DMA the host memory. We come back later on this part. This year, it was being the year of the BMC. There is a lot of presentation around BMC. Some people that published during Black Hat, so there is a guy from Immunity that introduced a lot of vulnerability in BMC from Dell, from DRAC, also from HP ILO, ourselves. And the people from Eclipsium that also present some stuff on the Cypermicro BMC. There is also our stuff, so that's published in the beginning of the year and in the middle of the year about how we can compromise the web server and how we can compromise also the firmware. The previous research that we was published allow us to make a good, to detect a good vulnerability. One of them, it's a bypass of the authentication on the web servers. And the other one was really interesting is the remote command execution, which allow us to have a direct access to the host memory with the DMA access. The last part of the previous research, it's how we can backdoor the ILO 4 firmware, and how you can add the malicious firmware in ILO 4 and be persistent and add some features to ILO. So all this stuff has been already presented, so feel free to be back on the link that we provide previously. Now, in terms of the red teaming, so I don't know for you, but I come from the pentest field and environment. So as usual, if you grab the password from IPMI, you can say, okay, I know the default password from your IPMI, so what I can do is just to reboot your server on the ISO, and then booting the system on this ISO and reach the sensitive data that not be encrypted on the hard drive. But if you do that, you are not really stealthy, and yeah, administrator can catch you easily because yeah, a reboot of the system was not really stealthy. Now, the nature of the vulnerabilities that we published previously was change the deal. Change the deal because we can really have a direct access to the memory, so we can, as more discrete, we don't need to reboot the system, we don't need to do something about the operating system, we just reach the host memory through ILO. And if you can backdoor the firmware, you can have a persistent way, and it's not correlate with the operating system. So you can store some malicious code in the ILO, reach the operating system without any interaction on the operating system. So that's why it's really stealthy and really discrete. If you can reach a RAM, that's really good for pen tester, because if you can do that, you know that PCI leech, for example, allow you this kind of attack. You can unlock the Windows authentication. You can recover some private key or some secret in the memory. So you can do a lot of things if you can reach directly the memory. By the way, if you know PCI leech, this tool can be interconnected with our attack. And maybe in the future, we can publish some result about this kind of tools. In the best world, what ILO infrastructure or what a real infrastructure should be look like is like that. You should have, it's not working, but you should have a dedicated enable administration VLAN. You should have a secure GMZ and an isolated backend. So usually no hackers can reach the admin VLAN. But if you can compromise the host and reach ILO, unfortunately, there is a lot of ILO has been exposed in internet. It's pretty weird, but it's like that. People just plug ILO in internet and you can reach it. So if you can break ILO, you can reach the operating system via the DMA. But if you already have an access to the ILO, you can also have a lateral movement from ILO and on the administration VLAN. So it means that you can compromise the other ILO interfaces, and if you compromise also the other ILO interfaces, you can compromise the host itself. And then you can have a really interesting lateral movement on the administration VLAN. That I say if you compromise ILO, but let's see, maybe you can compromise the host to reach ILO. So that's why Fabien maybe make more information about that.
Hi, everyone. So as Joffrey just told you, we first focused on compromising the ILO to then compromise the host. And for this specific research, we tried to see how to compromise the ILO directly from the host, so we can compromise the ILO from both sides. So a quick recap of the architecture of an HP server. So, well, there are, in fact, two really separated systems in the server. So the first on the left is the main CPU, so usually an Intel CPU with x86 architecture running a standard operating system. So here, a Linux kernel with all these processes in userland. And on the ILO side, so you have this ARM CPU running a real-time operating system called Integrity, which is not so different from the classical operating systems. You have a kernel and various tasks running in userland. So task is the name, in fact, for like processes in a normal operating system. And these two systems will communicate through the PCI Express link. So all which will be said in this part applies on ILO 4, but can also be valid for the new version ILO 5 with some slight changes. So to analyze how the host was able to communicate with the ILO, we first started to look at the available tooling. The Linux kernel has an open source driver called HP ILO, which exposes some character devices to communicate with ILO. It requires root permissions on the operating system to be allowed to talk with these devices. And on the other side, you also have HPE proprietary tools, such as HP on CFG, which allows to get and modify some configuration parameters of the ILO. And finally, when you download a firmware update for ILO, it embeds a binary which is called flash ILO 4 binary, which allows from the host to install a new firmware on the ILO. So it should be able also to understand the communication mechanism with the ILO. If we look at the ILO from a Linux point of view, it is simply a PCI device, which can be seen with the lspci command. And if we look at the main memory mapping, we have various chunks of memory which are used by these drivers, and which in fact allow to communicate with the ILO. The communication is done by channels. We have usually between 8 and 24 channels which are set up in these shared memory areas, and these channels have a simple FIFO structure. On the ILO side, there is a specific task which is called chief for channel interface, which is in charge of receiving the messages from the host and handling them. So what it does is simply waiting for messages from the host, dispatching the correct command to a specific command handler, or sending the command to another task because you can talk directly to other tasks. The message format is quite simple. You have a length, a command ID, a destination ID, which tells which task is the final destination, and finally, specific data for the command. And the important thing is that by default, there's no authentication, so the host is considered secure from the ILO. You can always, by default, talk to the ILO from the host. About the commands which are handled by Chief, we have more than 100 commands. Some are simple commands, such as getting, setting some configuration settings, the network configuration of the ILO, the server information, etc. And some are more dangerous. For example, you have command 70, which allows to read the ILO EEPROM containing all the factory setting of the ILO, which includes the default administrator password. Usually in ILO, this password is not changed because it's quite convenient. It's written on the server, so you can use it if you forgot the other passwords. There are commands also to flash a new firmware, so command 15 and 52. And finally, there are also commands to add new accounts on the ILO, including administrator accounts. So to show you how easy it's to communicate with ILO from Linux, here is a simple communication in 6 lines of Python, which use the command 70 I showed before to retrieve the content of the EEPROM. So you can see that with 6 lines of Python, you can retrieve the default administrator password stored in the EEPROM. So now that we studied these commands, we focused on the firmware update command because it was quite interesting for us. It involves complex file format parsing, it has various signature checks, and if we find a vulnerability in this command handling, we might be able to flash a modified firmware by bypassing the signature checks. And another advantage is that the firmware update process is available both from the host and from the web server interface of the ILO. So a vulnerability in it would be triggerable by both sides of the ILO. So let's have a look at the firmware update process. So first, when you decide to flash a new firmware, the firmware is sent to either Chief if you ask it by the host, or the web server if you ask it by the network interface. This firmware is sent to a new task which is called Fume, which is the firmware update manager. This task will perform a first validation of the file format and the whole signature of the firmware. It will then ask the integrity kernel to perform additional signature verifications. And if everything goes well, it will ask the SPI service to finally write the firmware on the SPI flash. So a recap of the firmware file format. So the firmware is basically composed of 3 blocks. First, there's a fingerprint header, then some certificates, and then the HP image blob, which is the actual firmware. In the fingerprint part, you simply have the hash tip and the signature of the whole HP image firmware. So this is this part which is handled by the Fume task. So this HP signed fingerprint header is passed line by line by Fume, and the hash and signatures element are verified. Then the hash of the HP image block is computed, and the signature is checked with the hard-coded HPE public key. If we look at the HP image block, it's in fact composed of 3 other blocks. There are the kernel and signature components, which are compressed and signed, and also a small bootloader, which is not compressed and not signed. It's an ARM assembly stub. During the boot process of the ILO, first the bootloader executes. It has code to load and verify the kernel signature. Then the kernel which will load and verify the userland signature, but the bootloader is never verified in the boot process. This is the verification of the signature of the userland and kernel images is done in the kernel. There is a specific kernel task called GKIMG, which exposes a specific resource to userland task. It also exposes 10 command handlers. And for example, command 2 allows a userland task to ask to verify the signature of the kernel and userland components. So it will first decrypt the embedded signature, it will compute a hash and compare to the decrypted signatures, and finally try to decompress the image to be sure the compression is okay. And we also found that there's a specific handler also to change the key used to verify the signature. It will be important later. So a quick recap about the signature check. In fact, signatures are checked in 3 different steps. First step in the Fume task, the whole HP image signature is checked. The second part in the kernel, in which userland and kernel images signature are also checked. And finally, when the ILO will boot, there's a kind of secure boot chain where kernel and userland signature are checked. But the bootloader is not signed, and the bootloader is never checked in the boot process. So it means that with a single userland vulnerability in ILO, we are able to write a new firmware on the flash by asking the SPI service. Then the bootloader can be modified to allow loading a kernel with an invalid signature. In turn, the kernel can be modified to allow the loading of a userland with an invalid signature. And finally, we can insert a backdoor in the ILO userland. So we then had a look at how Fume was handling the fingerprint header. And we quickly find this specific function in which it passes the header. And we saw this call to the function readline in red, in which local stack buffer is passed without any size. So this is not always a good idea. And if we look, in fact, at the readline function, we can see that there's no check on the size of the buffer. So there's here a trivial buffer overflow in the parsing of this header. This means that it could be exploited. We first tried to exploit it without code execution because it would be easier. So we wanted to just redirect the execution flow to simply bypass the signature validation and let Fume continue to flash the firmware. But in fact, we had the problem with the check in the kernel, which would fail, so we couldn't do that. So finally, we decided to exploit it with code execution by writing a specific shellcode. The chance here is that the ILO system does not have security mitigations such as ASLR, no NX. So a shellcode can be written in the firmware file, which is loaded at a fixed address in memory, and we can just jump on it. And then the shellcode content could simply be to talk to the SPI service to ask him to actually write the firmware on the flash. Or we can simply change the GK image key, resign the firmware with our own key, and let Fume continue the process normally. So this vulnerability has been reported to HP in May. It impacts both ILO 4, on which we did the research, and ILO 5, the new version. Patches have been available. It is both a remote and local code execution, because you can either exploit it from the web server of the ILO or from the host running on the server. So, now you can tell that, there are several vulnerabilities in ILO, it's dangerous, okay, I will disable it on my server. So here we have disabled the ILO on one of our servers, so you can see here that ILO 4 is disabled. But unfortunately, when you disable ILO, it only disables the network part on one side, but from the host, ILO is still running, you can still communicate with it. So here's the code example I showed before to retrieve the content of the ILO EEPROM. So even if you disable the ILO, you can still communicate with it on the host, you can still flash backdoor firmware and then, install your backdoor. So we already proved that firmware backdooring was possible. It was the subject of our previous presentation on ILO. We added, in fact, an endpoint in the web server to allow us to have direct read and write memory access on the host and install a memory-only backdoor. And now, with this new vulnerability, we are able to do it directly from the host, and even if ILO is disabled. So we can install a persistent host backdoor in the ILO hardware, and then this backdoor could push memory-only backdoors on the host. And now comes ILO 5, the new version of ILO. So I will let Alex tell you about that.
So yeah, in the middle of 2017, HP released a new version of servers, which is the generation 10 of HP servers, which embeds a new version of ILO systems. What we wanted to know, what were our motivation, was simply to assess the evolution of the attack surface. It was not a complete vulnerability research campaign, that's not what we were looking for. And our focus was really on a specific feature which could be a game changer for these servers, which is a silicon root of trust. They call it a silicon root of trust. It is something like a secure boot. So the idea is to have an hardware root of trust with their own processor, ASIC, which will validate the firmware of the ILOs first, and then the trust will be transmitted to the next steps. So we needed a new toy to do a research. We bought one entry-level server, not too expensive. It has Gen 10. It is a Gen 10, so it has ILO 5. And that's on this hardware that we are working. Just few quick check on the motherboard. We can see there is some memory on the below. On the top of the picture, we have the flash memory, the same as on the PS4 actually. And in the middle, we have the ILO chip. We didn't find information about this ILO chip specifically. From the firmware, we discovered it is built around Cortex A9 ARM processor, but we don't know what are its secure boot capabilities, its cryptographic capabilities. We don't know about that. Just some findings also. When we were researching some marking on the motherboard, we discovered some export or customs documents which may be linked to a Wistron Corporation, Chinese company that may be responsible for the design of the board. So we have a new system, so a new firmware format. We needed to analyze it. The firmware is 32 megabytes. It's wrapped into an HP image signed container, exactly like on ILO 4. It contains a boot block, 10,000 bytes at the end of the firmware. And at the beginning, we have a list of modules. There is 2 copies of each modules, most probably for fault tolerance when writing in NOR memory. Each module is described by reader and is, of course, signed. Just to give you a preview of the reader, here for a kernel, we have few important fields. At the very beginning and at the end, we have a magic. We have a header type, which will indicate what kind of module it is, if it's a kernel, userland, or one of the 2 bootloaders. We have the CRCs, and at the end of the module, we have possibly 2 signatures. All the modules we found only use 1 signature. Okay, so now we are able to parse the header. We are able to parse the list of all the modules that are embedded within the firmware. We saw there are 10 of them, including the boot block at the end. So just to give you a preview of the boot chain of the ILO 4 system. So we have the boot RAM, which is located inside the ASIC, which will pass the hand to secure microboots, then to NEBA 9, which in turn will go to the kernel, and then to the userland. We don't have any clues if they have developed this bootloader, secure microboot and NEBA 9 by themselves, or if they are part from, I don't know, another company's SDK. We don't know about that. If you have the information, we would be very interested. So now we are going to try to attack this secure boot. And we will begin by the very start of the boot chain, which is the boot RAM. Our guess about how it is working is that the boot RAM will init the DDR memory and map the whole firmware into the memory, at the top of the memory, at the I addresses. It will then first verify the signature from SMB0 header, the one at the very top of the memory, which will check the first 8,000 bytes. Then it will verify the signature from SMB1 header, and if everything is good, it will trigger the ARM reset vector and then start the execution of the first stage bootloader, secure microbot. It's only a guess about the behavior of the boot RAM. Now, the secure microboot is a minimalistic first stage bootloader. It does very few things, few CPU initializations. It seems to access some kind of persistent memory with some configuration information. Speaking about the processor, it's an ARM, but it doesn't use a trust zone at all. Some interesting point is that this first stage bootloader actually exposed a quite large API, something like 60 functions, and it will then load the second stage bootloader, which is neba 9 in the nominal behavior. When Secure Microboot loads the next stage bootloader, it is passed what we have called a configuration. It's like a job description. It tells you where in memory you have to look for the next module to load, what kind of modules you are looking for, where in memory you will load the header, the main body, the actual code of the next modules, some security parameters. We will come back to this point later. And to find the module in memory, it applies a quite basic algorithm, matching the start and end magic with the module types. Speaking about the types, parsing the array is quite simple. In this kernel configuration, we have 3 possible types that can be loaded, A, B, and C, and from few modules we can have the description of these different types. Another very important field of this kernel configuration is the security parameter. Actually, 2 bits are more important than the others. The first one tells you if the boot will be verbose or not, and the second one will tell you if you use or not the hardware crypto processor. This crypto processor is only used to compute the hash of the module for integrity. So, how the cryptographic integrity of the module is verified, or the signature is verified. So, as we saw before, up to 2 signatures can be used and stored in the header. The signature is a basic RSA one using a 4096-bit key. And at the end of Secure Microbot, we found a flat array of bignums, which actually contains the exponent that will be used, followed by 6 public keys. So, if you remember from the header, we said there is 2 index. Actually, this index will tell you which public keys you will select from your store to verify, to decrypt the signatures that are embedded in the header, and then to verify the hash that of the actual next module's body. So that's how it works. Something interesting we discovered while reversing is that when it computes the integrity of the next module, some fields of the header are not covered by the CRCs or the hash computation. So there's 4 bytes that are omitted from the header. So it was quite strange. We are a bit suspicious around it, and we were looking for. And actually, these 2 index fields are not covered by the integrity. It's kind of strange, but actually we didn't find some way to exploit these things. One hypothesis could be that it is used for post or cross signatures by different entities. But just for now, just keep in mind that the index fields look suspicious. So now we progress into the boot chain. We have bootrom has loaded Secure Microboot. Secure Microboot has loaded neba 9, and then neba 9 will try to load the kernel. Actually, to do that, it will reuse the primitives exposed by the Secure Microboot API. It will ask, it will call a function which is something like a DL open, and Secure Microboot will verify the signature of the kernel, load it into memory, and if everything is good, neba 9 will jump onto the kernel. Now we are in the kernel. Next step. So actually, ILO 5 kernel has almost the exact same code as the one that is present is Secure Microboot, but almost. The kernel only trusts 1 single public key, which is called the legacy key. It actually is the same as the one that is used to sign ILO 4 components. So back into ILO 5 kernel, we have functions that we have called load signature that will try to load one of the two signatures from the header. And actually, inside this function, there is kind of a broken logic. First, it will try to load the first signatures from index 1, and it can fail. And the next, it will try to load the second signature and load the legacy key from the second index. And our guess is that at this time, the developer made the hypothesis that even if the load legacy key failed for index 2, it means that the first one has succeeded for index 1, but which is actually false. So what happened? What can happen is actually the load legacy key will fail for index 1 and index 2, and the two signature fields will be left untouched. And at the end, the kernel will compare the hash value it has computed with the module it has loaded in memory with an untouched sig1 field. And actually, this time it is quite exploitable, yes. So all that we have to do to exploit this is we will extract the firmware, get ILO5 userland, decompress, insert whatever we want backdoor into it, and then recompress it. Then we will set index 1 and 2 to rogue values, update all the sizes and CRCs to be correct, and we will simply compute the cryptographic hash of our new backdoor userland, and we will update sig1 field with the hash value from above, just like that. And then we can use the vulnerabilities that Fabien presented to you, for example, to push the firmware, and it should work. Actually, not quite yet. We will see why. Actually, we screw up a little, big meme, and all that we got at that time was a blinking motherboard. The server wasn't started at all, but ILO services seems up like SSH or web server, but seems quite broken or unresponsive. We were not able to flash anymore a new firmware, so we were kind of stuck. We needed more information. When we were doing researches on ILO4, we had some serial output from our microservers. So that's what we did. We started probing some pins on top of ILO5 system to see if we can get the same serial outputs. So we got to a logic analyzer and started probing on the motherboard. Hopefully for us, there is 2 slots or 4 pins which provide serial output. One of them seems to be for the power management controller, the other one for the ILO systems. So yeah, we started plugging into this serial output, also to plug into the flash to write specific bits at some points. Just an example of the output of the power management controller, but more importantly, we get the logs of the ILO systems. And at the end of it, we found that there was some kind of error in the loading of the task of the ILO5 system. And using that information, we are able to see where were our mistakes, actually. Actually, we screwed up when we were backdooring the new userland. We had some bad decompression code that we had reversed back when we were doing some researches on ILO4 systems, and it induced a very late error in the health parser of the integrity system. So the system is half running, but not enough. And that's why the kernel does not pop some recovery FTP server. So we fixed everything. We flipped 1 byte directly writing in the NOR flash memory to force the kernel to enter into recovery mode, push a legitimate firmware to restore sane states, and then we fixed our decompression algorithm, which at the end was only LZ77. And also at the end we discovered that we doesn't need to recompress or use backdoor userland because we have enough room in the firmware to leave it uncompressed. So now we will show you a demo where we have a backdoor firmware. If we can switch to the video. Yep.
Okay, so here's the demo. You have the serial output, the host running Linux, and finally the attacker laptop. So if we first check the SSH banner of the ILO, everything is normal for now. And now on the Linux host, we will try to flash a backdoor firmware here. It embeds the exploit for the previous vulnerability in Fume, and we also modified it to change the 2 indexes to bypass the secure boot. So if we first try to flash it, well, it tells us that it can't flash it because the version is lower than the version currently installed, but well, if we ask him kindly, it will allow us to do the downgrade. So now the actual flashing starts. This part has been accelerated a bit because it takes a long time to send the firmware and to effectively flash it on the SPI flash. And well, when the flash is ended, the ILO reboots, and we can see that well, everything goes well. The ILO finally gets its IP address, and now if we check the SSH banner, we can see that we successfully changed the banner and thus compromised the ILO firmware.
Thank you. Thank you. So at this point, we're able to push whatever userland we want, inserting backdoor into web server component, SSH components, or whatever we want. We reported this to HPE at the beginning of September, and they released quite quickly a fix, ILO 5.1.37. They name it a local bypass of security restriction in firmware updates. But with this fix, we have some big uncertainty actually, because we reversed how they did the fix. So of course the kernel logic is fixed, so the logic error is corrected. But first stage and second stage bootloader are still totally unchanged. And we have actually legitimately signed vulnerable kernels, and what an attacker could do is to build some kind of Frankenstein firmware using all vulnerable kernel and new modules, new userland backdoor modules. So we don't know how they handle, or if they are able to handle the revocation of these vulnerable signed kernels. So it's a big issue. We have also tried to downgrade a firmware to update to a fixed version of the firmware, ILO 37, and then upgrade to a vulnerable version, and it works perfectly. So it's a big issue because we still have an attack vector at physical attack vector, like typical supply chain attack, but also logical. If a new vulnerability is found in the web server or anything, it could, and we can access the SPI flash memory, sorry, we can do the exact same thing. So to conclude, about first ILO 4 system, we have a very large attack surface, both on the administration and on the production side. Like Fabien demonstrated, we can attack ILO from the host as well, and that's very important. Unpatched systems are going to get ready. It's a dreamland for lateral movements. Network isolation is a must-have, but as we saw, it's not sufficient. These assets should really be monitored and up-to-date, and keep up-to-date very carefully. Some very simple hardening can be done. You can disable IPME overland. You can also disable XML data output, which will reduce some information leak. Speaking about ILO 5 now, more specifically, some good news and new features. IPME overland is disabled by default, which is great. There's new HTML console and lots of new features like backup things like that. But at the core, the system design is basically the same as ILO 4. It is still the integrity operating systems, but there's still no hardening or defacing death like we should expect, SLR or anything like that. And of course, we can expect more vulnerabilities in these codes. The silicon root of trust secure boot is clearly a step in the right direction. It should have been a killer feature to prevent long-term compromise of these assets, long-term compromise of the ILO 5 firmware. But actually, right now, it seems like totally hindered by a weak design and flawed implementation. And of course, there is these big questions about the possibility to revocate the signatures of vulnerable kernel. We've asked the questions to HPE many times, but we never received some answer on this point. Yeah, just before closing this talk, we'd like to thank the HPE PSRT team because during these last months, we have built some kind of good working relationship with them. We appreciate that. To thank you also our teams. Just give it a couple of days and we will publish the script and tools we have used for this study on our GitHub project for these ILO researches. Just before closing also, we'd like to share some quotes we found while reversing the code, something we always appreciate, the reversers. And also we would like to say hi to Andy, which is, he was here. And yeah, thank you very much for your attention. And if you have any questions now or during the conference, do not hesitate to come to us. Thank you.